So welcome to you all to my class on ring theory. So this class will be for postgraduate students for Presidency University, Kolkata. So in this course, we'll basically look upon few of the abstract algebraic things. So mostly we'll deal with algebra. So while dealing with algebra, we come across few of the topics in our undergraduate or even in our postgraduate studies like number theory, group theory, ring theory, field theory. So usually in our undergraduate studies, we all do have all those things, maybe at the very basic introductory level. But after that, we also had in linear algebra this vector space that we also study in our undergraduate level. But in the postgraduate level, we also have in algebra another generalization, you may say, of vector space that is known as module theory. So that is a complete picture of algebra in usual the normal studies of our algebra course. So out of which we have already started in our undergraduate level few of the things and few more will be done during this course. Okay. So the first question that usually comes to our mind is there any application of algebra? So of course, the question that haunted me from my maybe undergraduate studies when we study many of the algebraic structures, but at that time I didn't have much idea that what could be the applications of algebra. Let's start with few of the applications of linear algebra. So many of us are very fond of having or viewing or seeing the movies, animated movies. And you'll be surprised to know that this linear transformation, they play an important role in preparing or making this animated movies. So you can see that using this linear transformation, these images can be rotated, can be shrink, can be extended and all. So this linear transformation and geometry plays an important role in making this animated movies. So many of you might have heard about the term Matlab or Mathematica. So usually sometimes we do calculate many big things like for example say finding the eigenvalues of a very big matrix or dealing with an image in a matrix format, say maybe 1,000 by 1,000 matrix and then calculating some things on that matrix. So you can understand that writing a C programming will not be that easy for dealing with such a big matrix. So there is a software which is known as Matlab. It actually helps us in dealing with big datas, I mean big matrices and all. So you'll be surprised to know that this matrix is basically involved while having this software. And the MATLAB stands for Matrix Laboratory. So you can understand that how important is matrix for this software. So we sometimes send our email with many of the attachments and sometimes we make it a zip. That means we can compress the data or we sometimes we listen the songs in MP3 format or MP4 format, something like that. And you'll be surprised to know that while compressing our data, the computer binary data, we require linear algebra, the techniques of linear algebra, the theories from linear algebra to compress the data. So for data compression, linear algebra plays an important role. Now this term big data analysis is a very buzzword. So many people and many companies, they are going for big data analysis, analytics, etc. And you'll be surprised to know that while dealing with this big data, for example, suppose you are talking about some business, say for example Geo company, they are looking at how the business are doing for Geo mobile or the internet connection connectivity. So huge amount of data, say more than maybe 10 crore of people data they are looking at. So how to deal with that big data, and from that big data what could be their conclusion, whether their business is doing well or not. So the idea is you have to first collect the data and then you need to analyze the data, and from that analyzation or after analyzing this data you will have some kind of conclusion. And that for while this analyzing this data you require lots of techniques of linear algebra. So linear algebra plays an important role here, And in the course due time, if we find some time, we'll try to explore how this big data analysis plays an important role. And many companies nowadays, they are actually looking for big data scientists, I mean scientists who know this data science and all. So it's very important. And from Presidency University, every year many of the students, they go for big data analysis courses are offered here and there. And for that, the Python programming language plays an important role. So in the second year of your, I offer the cybersecurity course, the cryptography course, where I will explore few of the part of this Python language and also this big data analysis and how security plays an important role there. So there is another very important is communication. So you can understand that when we have our mobile phone, so usually when previously we usually had the landline. So I am sure that not many of you at your home do have this landline now. So that's being replaced by the mobile. So in mobile, there is no wire for communication. So it's a wireless communication. So some data, suppose you are making a call to your friend, then the data actually first your voice is converted into the binary language and then signals, and then the frequencies they are transmitted and through the air, and then some towers are there which receives your data, and then it sends to the proper mobile after hopping many of these towers, and then suddenly it will reach to the person to whom you are calling, and then again the signal will be converted into the sound and you listen that sound. So it's a quite complex mechanism that usually we do have, but we don't find any difficulties, and the sound qualities are nowadays very clear. But while moving from one place to another, while receiving the data by different towers, or even sometimes it's through satellite, you can understand that these signals, they travel a huge amount of distance. And during that period of time, this data may be distorted, but still we have a quite good quality of sound quality. How it's happening? And that's happening, there is one reason behind it, is due to the power of coding theory. And you'll be surprised to know that the linear codes, they are nothing but the element of a vector space. So linear coding theory, which actually if you have some error in between, then that linear code, few linear codes, they do have the power to correct itself. That means even if you have some mistake while traveling the data through the air or somewhere, if some mistakes or some distortion would be there, then also this linear coding technique theories are there which will help to correct the errors. So if certain amount of errors are happened there, then only it can correct. So it's a known as error correcting codes, and there are many error correcting codes which actually involves lots of linear algebra. So everywhere you can see that linear algebra is there. Now, if you look at the other part, that is the abstract algebra and number theory, again the same question comes to our mind, that is there any application of this abstract algebra or number theory? The biggest application of number theory is in cybersecurity. So usually we are very much nowadays fond of our mobile. So when we get up, before going for a bus, we first have a look at the whether any new message or any status or any new email that comes to your mobile or your laptop or not. So before going for bus, we usually first go for our mobile. When the day goes on, then also we are very busy with our mobile, like chatting with others, or seeing the newspaper, or sending emails, or even in our leisure period of time, we play with our mobile, we listen songs, we see movies, and so on. So I mean, in our whole day, the mobile plays an important role. Not only that, at our bedtime also we stay busy with our mobile. And all the things are done very easily by installing lots of apps, and that makes our life so easy that a child can even operate a mobile even in a better way than us, very easily. And as a result, we feel that we are very confident that we can use or we can achieve anything using mobile. But at the same time, we should also keep in mind that with the advancement of science and technology, there might be some drawbacks. So now all the data are being digitalized, and as a result, if that data is gone to some wrong hand, then we may be at a danger. And that happens, and as a result, we need some security of our digital data. And here, number theory and abstract algebra plays an important role. So the term cryptography comes into play here, which actually gives us the confidence that when the message are being transmitted from one place to another, it should not be very easily gone to the wrong hand. For example, when we chat with each other, you might have heard about the term end-to-end encryption. And due to this end-to-end encryption, the WhatsApp, they claims that even the company itself won't be able to read what other messages are being sent from one person to another. So here the term cryptography comes into play, and in our fourth semester in Presidency University, I offer a course solely on cryptography. So that will deal with the practical applications of number theory, abstract algebra, and linear algebra. Okay. Also, when we do transaction, online transaction, we buy many things online, and sometimes we pay using our card, credit card, or debit card. There also the confidence that we get. So everything our the all the card details, the password, etc., are being sent online. But how we get this confidence that nobody else should get it? So here also the abstract algebra and number theory plays an important role. So while a server and a client communication, for example, suppose you are searching something, say I am searching for a say football. I am searching for a football. I want to buy some football, and some companies are selling that football. So when in the Google I search for a company or for a product, then when I search it, it gives a lot of names. And when I click on some of these names, then it goes into the server or the web page of that particular company. Then how your machine be sure that that company is that secure? So while communicating with each other, we call it client and server. It first makes a kind of handshaking, and through this handshaking it comes to know that okay, to whom you are communicating is a valid or a genuine one. So here also, this for handshaking purpose, abstract algebra and number theory plays an important role. And you'll be surprised to know that with these numbers, mostly the prime numbers plays the most important role. And this is an example of 904 digits long prime number. So it's a huge prime number. You can see that. And if I ask you, can you please check whether this number is prime or not? But you won't be able to do that except to just have a look at the last digit. Since this is an odd number, you may not be that sure that whether this is a prime, but suddenly this is not even. Up to that, you can do that. But believe me, this is a prime number, and it's not very difficult to get this big prime numbers using the theories of abstract algebra. So in my undergraduate course, I took a course on number theory. There I have given the algorithms how this could be done very efficiently, very easily, that a simple laptop can find this big prime numbers maybe within 30 seconds or 40 seconds. So that hands-on experience that you might have seen when you will be in the fourth semester, where you will find that these big numbers, how to find these big numbers very easily. So there, how to find these big numbers, there also we have the very strong motivation as well as very strong support from abstract algebra as well as linear algebra. Now, just have a look at a very historical development of group theory, because in my course I will be going for ring theory. So I will also have a very quick overview of the very historical development of ring theory. But I want to point out very few very interesting important results that we usually have a kind of misconception. Okay, so when we talk about group, so usually few terms comes into play, like closure property, associativity, identity, and inverse. So these four properties usually having on a non-empty set, if we have a kind of binary composition, then we call this non-empty set with this binary composition satisfying few properties, few axioms, we call it group. And these definitions, they are called axiomatic definitions, and these axiomatic definitions were actually given by these two big people, Jordan and Dirac. So you can just have a look at this timing around 1870, this, or around 1882. So at least around 1870, during that time, these axiomatic definitions were introduced. Okay. Now, when we go a little bit deeper into the study of group theory, then we usually have few of the theorems and terms like Lagrange's theorem, abelian group, normal subgroup, Cauchy's theorem, Cayley's theorem, and etc. Now, if I ask you a very simple question, who invented or who for the first time gave the theorem of Lagrange's theorem? So I am sure that you all know, or you at least remember, what is the statement for Lagrange's theorem. So it depends on it's actually involved this finite group, and for a finite group, the order of a subgroup must divide the order of the group. So it very much involved with the definition of groups. But if you look at the time during which Lagrange's was there, it's around 1736 to 1813. And if you ask this question, who gave the Lagrange's theorem, the first answer that comes to our mind is certainly Lagrange should give the definition or give the theorem. But if you look at the definition of group theory, so the axiomatic definition of group theory came around 1870, but Lagrange's was with us from 1736 to 1813. That means Lagrange's did not have any idea about the axiomatic definition of group theory. Then unless a person who knows nothing about the definition, how come he can give the definition or give a theorem like Lagrange's theorem? Similar thing for abelian group. If I ask you the question, who for the first time coined the term abelian, certainly your answer will be Abel has given this definition or given this term. But if you again, surprisingly, 1802 to 1829, see, it's much earlier than 1870. Similarly, it's assumed that Galois gave the coined the term normal subgroup, and again for Galois is 1811 to 1832, is much before 1870. Similarly, for Cauchy, it's this Cauchy's theorem is 1846, and even for Cayley's theorem is 1854. It's much before the definition of axiomatic definition of group theory. So it's quite surprising. Then how come the Lagrange's theorem came into picture, how the term abelian group came into picture, how the normal subgroup came into picture without having the definition of the formal definition or the axiomatic definition of group? So it's quite interesting. So in this class, I'm not going to go very detailed about all this information, but for a Lagrange's theorem, I have few interesting information, but for Lagrange's theorem particularly, I'll just give you, I will touch upon few of the interesting facts. So just have a look at the life of Lagrange. It's quite motivating for the mathematics students. So he was a French mathematician, and he did not show any interest for mathematics until he was 17. So till at the age of 17, he didn't show any kind of interest towards mathematics, but certainly within 2 years it became a very big change for Lagrange. From his 17, he alone threw himself into mathematical studies. So at the age of 19, he wrote a letter to Euler. So you all know about Euler. So it's a isoperimetrical problem. He solved an isoperimetrical problem, which was kind of an open problem for half a century, and he solved this problem at the age of 19. So he worked on problems on analytical geometry, algebra, theory of numbers, differential equation, mechanics, astronomy, and many others. But interestingly, we all heard about the term Wilson's theorem. So again, the same question, who gave the Wilson's theorem for the first time? And you will be surprised to know that Lagrange gave the first proof of Wilson's theorem. It's not Wilson's who gave the proof of the Wilson's theorem, but it's the Lagrange who gave for the first time the proof of Wilson's theorem in 1771. And it's from the evidence, it's also knows that in calculus you might have heard about the term Leibniz, and it is believed that Leibniz also aware of the fact of the proof of Wilson's theorem even 1 century earlier. So Leibniz may be the first person who gave the proof of Wilson's theorem even maybe 1 century before 1771. But Leibniz did not publish that work. Okay. So here the first interesting fact is that Wilson's theorem was first, I mean, formally proved or published proof was given by French mathematician Lagrange's, and it's not by Wilson's. Okay. So if you go to the statement of Lagrange's theorem, it says that for any finite group, the order of every subgroup H of G divides the order of group. So that we all know. But Lagrange's did not prove Lagrange's theorem in its general form. He stated that if a polynomial in n variables has its variables permuted in all n factorial ways, the number of different polynomials that are obtained is always a factor of n factorial. So in that form, he actually stated Lagrange's theorem for a very particular case of polynomials, dealing with polynomial variables, and while calculating something related to polynomial variables, he gave the result in terms of n factorial and the something that divides n factorial. The number of such polynomials is indexed in the symmetric group Sn of the subgroup H of permutation that preserves the polynomial. So with that respect, Lagrange's actually gave the statement of the theorem that usually we call it Lagrange's theorem. So Lagrange's did not have any idea about the actual statement that we usually do in our this statement. So this is not actually given by Lagrange's, but Lagrange's actually proved for this result. Then it's Gauss who actually proved Lagrange's theorem for a special case of ZP star. So we all know that the ZP star, what is ZP star? This is the group of all units. That means if you just remove the zero element from ZP, then you will have all the elements, and with respect to multiplication, we'll all know that ZP star forms a group. And Gauss actually proved Lagrange's version of the theorem as a special case of ZP star. So again, you can see that that is not the general form that we usually study today. Then Cauchy proved Lagrange's theorem for the symmetric group Sn. So see, at the time of Cauchy, the symmetric group, I mean the definition of group theory was not known, but still people dealt with the group of all symmetries and all, and the permutations group and all. So Cauchy gave the proof for the permutation group Sn, the symmetric group Sn. And finally, Jordan, who actually proved the Lagrange's theorem for the case of any permutation group in 1861. And at the end, Jordan finally gave the name as Lagrange's theorem when, as you understand, that Jordan and Dirac were the forefather for considering the axiomatic definition of the group theory. So Jordan, for the first time, he actually tried to find who was the person who first dealt with this kind of the statement which is related to the today's statement. So Jordan actually gave the name, it should be after Lagrange's, and that's why today what we think that Lagrange's gave the Lagrange's theorem is not correct. It's the Jordan who actually first gave the title or the gave the name that it should be a Lagrange's theorem. And that's why, I mean, in Jordan actually did many things like for normal subgroup also, or for abelian group also, he gave the name actually. Although, so Jordan actually tried to find historically who was the first person who coined the term, or who at least in some other context used that concept. So that's why Jordan, he was a very great person. He was a great mathematician, as well as he was a person who actually gave the actual credit to the person, and that actually misleads us. So it's not Abel who gave the Abelian group. It's not Galois who coined the this normal subgroup. It's not even Cauchy. It's not even Cayley who gave the actual statement of the theorem. So it's quite interesting. So I have other facts also, but in my class I'm not going for the details of other things, but I'm directly going to the history of basic, very brief history of ring theory. But before that, let me explain that in group theory, the group theory was actually developed from three different subjects. It had some group theoretic, so solving the equations, algebraic equations at the end of 18th century, leading to the study of permutations groups. Again, from geometrical viewpoint from 19th century, again from number theoretic viewpoint from the end of 18th century. And these big guys like Lobachevsky, Gauss, Mobius, or Euler, Gauss, and from algebraic equations. So you all know about Lagrange, Abel, Galois, Jordan, Dirac, Cauchy, Raffini. So they are all great people who actually helped in developing the subject group theory. So you can see that there are three different ways through which the group theory actually developed in today's form. So now let's have a look at the ring theory, history of ring theory. So usually in today's form, that the axiomatic definition, it's the Amy Noether. She was a female mathematician, one of the greatest mathematician in the field of algebra. And in 1921, Amy Noether gave a modern axiomatic definition of commutative rings. Mind that she gave the definition of commutative rings without one or with one. So here also we had a very interesting topic like the formal development of ring theory actually had two branches initially. So it was like a commutative group and a non-commutative, sorry, commutative ring and non-commutative ring. So both of them actually they were developed in a from different perspective. So at the very beginning, it was like commutative ring and non-commutative rings. They developed in a different way. But after 1930 and all, when Amy Noether and others they came into picture, then they found that okay, for non-commutative and for commutative ring, both of them they do have few similar properties, and as a result, it came into picture as a ring theory, the theory of rings, where it will have two branches, but they are many common things are there for both commutative ring as well as non-commutative ring. So though Amy Noether gave the first formal axiomatic definition of rings, but Dedicant is considered to be the father of ring theory, who actually gave the defined the concept of ring for integers of a number field. So as I mentioned, number theory plays an important role in the development of ring theory. So you all heard about the famous last theorem, right? So it was like more than 300 years, it was considered to be an open problem. And while solving or disproving or proving this result, many branches of mathematics came into picture. For example, algebraic number theory, algebraic geometry, and ring theory. So ring theory you can consider as a byproduct of this theorem. And Dedekind was one of the person who actually deals with that number theoretic concepts. And while dealing with number theory, he for the first time defined the concepts of rings, but in case of integers in of a number field, and he introduced the term ideal. So you can understand that even the formal definition of ring, we had the concept of ideals. Okay, another name, it's a Hilbert. So you all heard about the Hilbert, and you know that Hilbert basis theorem. So that's one of the great work for number ring theory. So Hilbert actually coined the term Zerlings, and from that the ring theory term, the number rings, and he is considered to be the first person who coined the term ring. So it was around 1892, and you can see that in 1921 the formal definition of ring came into picture. But before that, Hilbert coined the term ring, but in a different perspective. So all three of them, they actually worked for commutative rings, and they developed the ideas for many ideas for commutative rings and all. But on the other hand, Hamilton, so you can see that much earlier than the formal definition of ring, so he he conceptualized the whole thing uh, in the form of the generalization of complex numbers. As a result, some non-commutative properties like quaternion rings, they came into picture. See, he also gave the idea of vector space. So you can also understand that quaternion rings are basically then examples of non-commutative rings, but he had the idea how to generalize the idea of complex numbers, and you can understand how they can be done. Another guy, this Kelly, he actually introduced the concepts of matrix addition and multiplication. As a result, you can understand that we today's scenario, we know that matrix multiplication is non-commutative. As a result, we have some examples of matrix ring and all. So they are basically, this Hamilton and Cayley, they are basically gave us the impetus for non-commutative rings. And after 1930, both the subjects, they actually merge together to form a theory of rings. And where as a branch of this theory of rings, somebody is interested on maybe commutative rings, somebody may be non-commutative rings, but at the end it was found that many of the results are common for both of them. So as a result, in today's scenario, we call it as a ring theory. So in this class, we basically deal with only ring theory, but I will try my best to explore few of the other topics like real analysis, how ring theory and real analysis are involved, how topology and ring theory are involved, how complex analysis plays an important role with ring theory, how graph theories are important, how algebraic geometry plays an important role while studying ring theory, and also of course cybersecurity, how it plays an important role, and no doubt this number theory, which is considered to be the one of the reasons of generating this ring theory, how this number theory and ring theories are related. So apparently, when we study ring theory or abstract algebra, we see that this topic as a whole is a kind of independent topic. So when we study ring theory or in some abstract algebra, we sometimes feel that okay, real analysis is a different topic, and abstract algebra is a different topic, and there may not be some connection. But if you find, or if you have a look upon few of the interesting results, then you will understand that okay, all these topics are very much interrelated. Many examples of rings can be found by using lots of results of other topics like real analysis, topology, complex analysis, graph theory, and etc. So in this course, I will try my best to give you at least some glimpse of idea how the different topics are related with one another, and then you will find it more interesting that how and why should we study ring theory, or why should we study abstract algebra, but not, it's not like other topics are independent. So all of them are very much closely connected. And in this course, I will also emphasize few of the competitive exams as well as few of the interview questions. So while you go for some interview questions, especially for institutes, there, if they usually ask you that which topic that you have studied for today's interview, or which is your comfort zone. So somebody says that algebra, then suddenly he will be asked questions from algebra, but you will be surprised to know that it's not only algebra. The persons who are going to ask you the questions, he usually make you change to some shift from algebra to other topics. So I will show in this class that how or what are the questions that may be asked, so that from ring theory you will certainly be transferred into some other topic like real analysis or measure theory or functional analysis or topology or complex analysis and all. For example, suppose you all know few of the examples of rings. So you all know few of the examples, very interesting examples. So I assume that in your undergraduate course you have studied few of the terms, like you all know what is the, okay, what is the definition of rings. So I'm not going to the definition of rings and all, but I assume that you all know what is the definition of ring. Okay, so few examples, if we consider few examples, for example, if I have say X is a non-empty set, say X is a non-empty set, and say R be any ring, be any ring. Now I consider another ring, say R. Now I consider a set, okay, all functions from X to R. Okay, so this is ring and this is a non-empty set. Now I consider all functions from X to R. So now this R is my set. Now on R I say define this addition and multiplication like this. So F plus G of X. Now I am sure that you understand that this plus and this plus, they are not the same. Now you are matured enough to distinguish between this plus and this plus. So this plus is basically for the ring R and this plus is for the my script ring R. So how it's defined? This is defined as fx plus gx, and now I need to define f dot gx, and this is nothing but fx dot gx. Now you are matured enough to understand that this dot and this dot, they are not same, because fx and gx, they are elements of R, and this dot is basically for this dot. Okay, and this dot is basically the dot for this script R. So now I hope that you all understand and you are matured enough to understand the dots or the plus are for which set. So this is for all X belongs to X. Okay. Now with respect to this plus and dot, you can say that this forms a ring, and I'm sure that in your undergraduate level, with respect to this plus and dot, you can say that this forms a ring, forms a ring. Now, this is quite a general format, like X is any non-empty set and R is any ring. Now, if I ask you the question whether this, what would be the condition, what extra condition should you impose on this R so that this script R will become a commutative ring? Certainly, we can answer that, okay, if R is a commutative ring, then the script R will also be a commutative ring, because see, you can understand that this scriptor actually depends on the elements of R. Okay, so if this is commutative, then this will become also commutative. Now if I ask you the question whether the scriptor is a ring with 1, so that also depends whether your this original R is with 1 or not. Now instead of just a non-empty set, if I consider, instead of non-empty set, if I consider X to be as my open interval 0 1, and the ring R, if I replaced it by our real R, so this is R plus dot, then you can see that this script R, usually we denote it by C01, and if I replace this the normal function as continuous functions, that means C01 is nothing but collection of all real valued continuous functions. That means all functions from the closed interval 0 1 to R, such that f is continuous. Then if I define the same 0 1 as same plus and dot as I defined just earlier. So now what I am doing, I am just giving a particular value of x. So previously x was just a non-empty set and R was just a ring. Now I am replacing it by x by a closed interval 0 1 and R to be a ring, or you can say the field of real numbers. So certainly we call it C01, but here the f was just a function, but now f is all continuous functions. So that means real valued continuous functions from the 0 1 interval, closed interval 0 1. And that scriptor then will have a special name, we call it C01. So you can understand that C01 now it's also a ring. So it's a commutative ring with one. With one means multiplicative identity. So you all know that in a ring you might have the multiplicative identity or you may not have a multiplicative identity. So I think the basic terms you should just recapitulate with from your earlier studies, then it will be quite clear those who are just listening for the first time. But I'm sure that in your undergraduate level you studied all those things, and just if you forget this, just you read once again, then you will remember all the basic definitions. Okay. So this is a commutative ring with one, that means with multiplicative identity. Why I am talking about this particular ring is that it gives you basically the connection between real analysis and the ring theory. So now you can understand that if f is a continuous function and g is a continuous function, then with respect to this addition, first you need to show f plus g is also a continuous function from 0 1 to r, right? And to prove that if f is a continuous function, g is a continuous function, to show that if both of them are continuous function, then f plus g is also continuous function, you can very easily prove it by using your epsilon delta definition. I hope that you all remember. Similarly, you can also prove f dot g is also a continuous function from 0 1 to r. So that is the first basic requirement to prove it that this is a ring. And here the properties of epsilon and delta as the definition of the f and g are playing an important role here with respect to that epsilon and delta. By using this property, I am sure that at your very undergraduate level you all prove this kind of results, that f g, f plus g, f dot g, they are all continuous functions if both f and g are continuous functions, and the proofs are very easy. But what I want to emphasize is that you are studying here the ring theory, and if you understand or if you have the idea that okay, it's a ring theory, so we may forget the definitions of epsilon delta definition, then you are certainly wrong. And when you will appear for some interview for some good institution, they will certainly ask you this kind of question to check whether you only love algebra or you have some basic idea with algebra along with some other topics. For example, if somebody will give the option that he is comfortable in real analysis, then certainly he will also from continuity, certainly they may ask you a question, can you construct something from this continuous functions as a ring or as a group something? And then his question will be certainly shifted from analysis, real analysis into algebra. So at least two fields. What I am trying to say that while you are appearing for some examination or for some competitive exams, the most important thing is that you should have at least two topics at your hand. So you may be very good in algebra, but you should also well acquainted with other topic, for example, complex analysis or functional analysis or maybe real analysis or topology. Okay, the same thing. How I will associate the ring theory with topology? Very simple way. So here you can see that here x was my closed interval 0 1. So those who have started studying the topology might have heard about the term compact, maybe housed of topological spaces. So here this is a closed interval. It has some special property over the non-empty set X. So if instead of this X to be a compact Hausdorff space, and if we consider as an R, that means my R is like from X, all functions, all continuous functions from X to R, such that F is continuous. And instead, if I have, this is initially when I started, it was like my just a non-empty set, but now if I have this compact and Hausdorff space, or even only compact, then what extra properties that we'll get? So we know that that is certainly a ring, but what extra property that we get over the normal ring? So then you can understand that a term from topology came into picture, and then after that you may be asked with questions with the topological spaces. For example, if I want to convert the whole thing from to the viewpoint of complex analysis, I may think of, say, R, maybe the F, such that F is an analytic function. So those who have started studying this complex analysis, by the meantime, you might have heard about the term analytic function. You know, or if you don't know, then after a few days, you will certainly come with this term analytic functions. So this is in a complex plane. Now, if F is the collection of all analytic functions, then with respect to plus and dot, that also forms a ring. Certainly, this plus and dot will have special meaning. But again, then we'll find that this is a former ring. And if I ask you this question, whether that ring R plus dot is R plus dot an integral domain. So in your undergraduate level, I am sure that you heard about the term integral domain. So what does it mean? That means a commutative ring without any zero divisor. So if you forget this term integral domain, I request all of you to please go through your undergraduate level book and or Google it integral domain. You will find that what is the definition of integral domain. So many of the authors, they consider integral domain to be a commutative ring with one having no zero divisor. Some of the authors, they drop that with one property. That means only commutative ring without any zero divisor is said to be integral domain. So in my classes, I will consider, or in my book, I consider this integral domain to be a commutative ring with one. Okay. So without having any zero divisor. But if I ask you this question, whether this R, that means collection of all analytic functions with respect to properly defined addition and dot, whether that forms an integral domain, if you are going to prove that, then you will understand that you will require many of the complex analysis results. So it would be a kind of sequence, it would be a kind of limit points, and all many of the things will be involved here to answer this kind of question. So you can understand that I will ask a simple question from algebra, but to answer that question, you should have at least a good knowledge of complex analysis. That means you cannot neglect that I am very good in algebra. That does not mean that you will be able to crack the interviews like NBHM or TIFR or many other places, ISI. So where along with the question, you'll also be asked from a question from a different field. And in this class, I'll basically try to show how this, in this course, not this class, I will try to show how these different fields are important. Okay. For example, instead of having this analytic function, you may have this measurable functions. So very soon you will all be acquainted with the measure theory, and then if I consider the class of all measurable functions, or maybe from or differentiable functions, then you can understand a flavor of analysis, complex analysis, topology all come into play. Again, there is a very good connection with algebraic geometry and maybe topology. So if I find some time in my course, I will show how Zariski topology. You just Google it and you will find this Zariski topology is an important play an important role how this algebraic geometry and topologies are important. Topology and ring theory, how they are connected. So just try to Google it. In my class, in my this course, I will try to explore how Zariski topology plays an important role here. So from number theoretic viewpoint, you can understand that the basic idea of ring theory actually evolved through solving few of the problems of number theory. So number theory plays certainly an important role. And surprisingly, you will also heard about the term graph theory. Graph theory. So it's you might have heard this in your undergraduate level, or at least in your postgraduate level. You will also have graph theory in your syllabus, and you will be surprised to know that this graph theory and the ring theory, they may be connected, and many properties of rings can also be uh, very easily found out by exploring the properties of graph and vice versa. So the properties of graph can be uh, evolved using ring theory, and the properties of ring can also be evolved through graph theory. So in this course I will try to explore few of the different areas that you are basically studying, and how ring theory plays an important role in solving or in dealing with all these properties. So that's quite interesting, and that would be quite important. And in this course I will also go through few of the problems that usually come in the very competitive exams like NET, GATE, or TIFR or somewhere. So we will bring out, or we'll put forward few of these problems and try to solve how that could be solved. Okay, so with this introduction, let me start the very basic things like ideas and subrings. So now we assume that we have all, we know that what is a ring. So say R plus dot is my ring. Now what is subring? So subring, as I mentioned, is nothing but if I have a ring and a non-empty subset S, suppose R plus dot is a ring, like subgroup, subring is also similar concept, that with respect to that plus and dot with restriction to S, that plus and dot itself with respect to that S and plus a dot itself forms a ring. So here S is a subset of R, and with respect to that restricted operation plus and dot, restricted means, so this plus and dot are defined on R, but here the plus and dot will be defined on S. That means you are basically restricting this plus and dot, this binary composition, over this set S. And if with respect to this plus and dot, if you find that this S plus dot itself forms a ring, then we called S as a subring of R. So how to check whether a non-empty set S with respect to this same plus and dot forms a ring or not? This idea is very simple. If you S suppose is a non-empty set and take any two elements AB from S, check whether A minus B is within that S. So the same property to check whether it's a subgroup or not. And then with respect to multiplication, I need to check whether with respect to product also, that also within S or not. That means I will take any two elements, say AB belongs to S, check if A minus B belongs to S and A dot B belongs to S. And it should not be like for one, two elements. it should be for all AB belongs to S. If this property is satisfied, we call that S to be a subring of R. Okay. So as I mentioned earlier, that a ring R may be with one or may not be with one. That means maybe with identity or may not be with identity. For example, if I have this R plus dot, suppose this is my ring Z plus dot, and as you understand from Hilbert idea, that he actually gave this concepts of ring. So not Hilbert, it's by Dedekind who actually gave the idea of ring by studying the properties of Z. So with studying the Z, that means integers with respect to addition and multiplication, the concepts of ring actually evolved. So here, if I consider R to be Z plus dot and 2Z plus dot set of all even integers, we see that 2Z plus dot is a subring of Z plus dot. So it has the multiplicative identity as 1, but the subring may not have any multiplicative identity. So here 2Z plus dot does not have any multiplicative identity. So in this course, I will basically means identity in ring theory, identity meaning the identity with respect to multiplication. So with respect to multiplication, and zero elements we means with respect to addition, the identity element with respect to addition. So throughout this course, I will with identity, or sometimes I will write it with 1. So with 1 means the ring having identity elements, that means with multiplicative identity elements. And when I need to talk about the 0 element, that means the additive identity element, I will represent it by 0 element or sometimes by 0. Okay. So we see that the ring may be with identity or may not be with identity. Now there are few interesting examples, like this is a ring and this is a subring. Suppose 1R is the identity, that means multiplicative identity of the ring R, and 1 is the multiplicative identity of the subring S. Now the question is 1R equal to 1S? If you think quite properly, then you can see that it may happen that 1S may not be same as 1R. Okay, so I need to have an example. So I'm giving you as an exercise to check whether 1R is equal to 1S or not. My answer, I'm giving you the answer, but it's your turn to find an example where 1S is not equal to 1R. Okay, so it may happen that a ring R and say S is a subring of this. I'm giving you another question, that the ring has no identity. Identity means multiplicative identity. But is it possible that the subring has multiplicative identity? That means the ring R has no identity, but the subring has identity. So I'm just giving you an example here. Say I consider, say, Z cross 2Z. So this is my R. So you can understand that there is no identity for R because you cannot have an identity element here. But if you consider this subring as this, then you can understand that 1 comma 0 is the identity of this, but it has no identity. So it may also happen that R does not have an identity element, but S might have an identity element. In my previous example, both of them, they do have identity elements, but the identity elements are different. So that's the question that I am asking you for this. So maybe in the next class I will explain, or you can send me email or you can comment it what would be the answer for this. Okay. So with respect to the subring, there is another concept known as ideal. I'm sure in your undergraduate level you might have heard this term ideal, but you may not study it in details, or maybe in some places this ideal is not within the syllabus. So let me explain what does it mean. So again, R is there and I is a non-empty subset. But though you may not have ideal at your syllabus, but in group you must have normal subgroup at your syllabus. So in case of ring, the ideal plays the same role as the normal subgroup in group. So the concept of ideal is almost similar to the concept of normal subgroup as in group. So you can understand in a group, if you have a normal subgroup, you have the quotient idea. Say if H is a normal subgroup, then you have the idea of quotient. And then with respect to quotient, that also forms a group. You can always quotient by any non-empty subset of G. Say H is any non-empty subset of G. You can always quotient like this. G quotient H, you can always make it a quotient. But to have an algebraic structure, this quotient has to be, this H has to be a normal subgroup. So if unless if you consider H to be any subgroup, then also the quotient is defined. But unless you have H to be a normal subgroup, this quotient will not have a group structure. So to achieve the group structure, unless, so algebraists are not very much interested only with a set. Unless you have some algebraic structure on it, the algebraists won't find any such interest. So when you consider H to be just a subset or any non-empty subgroup or any subgroup, then may not be G quotient H have a group structure. But if you have H to be a normal subgroup, then suddenly G quotient H have a subgroup, have a group structure, and that group is known as quotient, the group by quotiented by H and all. So you know all the properties of this. So in case of ring, the similar concept that is known as ideal. So let me check what does it mean. So ideal means first it has to be a subring. That means this properties has to be satisfied, like A minus B must be here. But some extra properties has to be satisfied. For example, I need to take any element R from the ring R. Note that this element R may be from I. Okay. So from this, I first take an R. From this R, I will make a kind of multiplication. So what does it mean? I will take the multiplication from left maybe. So take R and then multiply it with A. If for any R belongs to R and for any A belongs to I, if R A belongs to I, for all R belongs to R, for all A belongs to I, then I call it left ideal, because I am multiplying it from the left side. If the same thing happens if A R, that means A into R belongs to I, for all R belongs to R, for all A belongs to I, then I call it right ideal. And if both of them are satisfied, for all A belongs to I, for all R belongs to R, then I call it ideal. Okay. So you can understand, for a commutative ring, both left ideal and the right ideal, they are basically the same. For a commutative ring, we just consider about ideal. But for non-commutative ring, we may have the concepts of both left ideal as well as right ideal. So let's have a look at the meaning of this. What does it mean? So for example, suppose I take the ring Z plus dot and I consider 2Z plus dot. So as I mentioned, take 2Z means even integers, take two even integer, then suddenly if you subtract them, then a minus b will also be an even integer. Now to check whether this forms an ideal or not, I need to take any integer. Say n is any integer, maybe even or odd. But if I multiply n with a, note that a is an even integer and n is any integer. But if I multiply them, suddenly this whole integer n into a, that also an even integer. That means if you multiply n from the left with a, then also it becomes an even integer. Whether n is even or odd, it doesn't matter. That means if I multiply from left with n any integer, still that becomes an even integer. That means that lie within 2z. As a result, that gives me the idea of ideal. Since this is a commutative ring, its left ideal is checking whether it's a left ideal is sufficient, because left ideal will also imply the right ideal. As a result, this is an example of an ideal. Okay. Now I need to check for a non-commutative ring. So I know that example of a non-commutative ring will certainly be M2R plus dot, set of all 2 by 2 matrices where the entries are from R. Now let us consider say I1. I1 is nothing but say AB 00, such that AB belongs to R. Now with respect to usual addition and multiplication, you can check that this is a left ideal. So this is a left ideal, but not a right ideal. Similarly, if I consider I2, if I write like this, such that AB belongs to R, is a right ideal but not a left ideal. So now you can understand, you can check it. It's very easy to check. Now if I consider I3, like this, A000, such that A belongs to R. So this is an example of a left ideal. So here I have taken only A here, and here I have taken A here. Okay. So it was a left ideal but not a right ideal. This is an example of a right ideal but a not left ideal. But now if I consider only A here, and if I ask you the question whether this is a left ideal or right ideal or both sided ideal, you will readily, most of you will readily answer me that I3 is a both sided ideal. But this is actually wrong. But it actually gives you a kind of motivate you, provoke you to give this answer. So this is neither left ideal nor right ideal. So that's quite interesting. So this is, though it looks very simple, and you may see that it does not have this part or this does not have this part, it should be both sided ideal. But I3 is neither a left ideal nor a right ideal of M2R. That's quite interesting. So it's quite interesting because that's a non-commutative ring. So you might have left ideal, right ideal, and I see that I3 is not a both sided ideal. Now, if I ask you a question, can you give me a both-sided ideal in R3 into R? So my question is, can you find can you find a both-sided ideal in M2R? So that's the question. That's very interesting question. Okay, let's try to see. Suppose I consider I1 to be this. I want to be this, nothing. So all the zero of R means real zero. Okay. My question is I1 a both-sided ideal? What will be your answer? Could somebody give me this? Is I1 a both-sided ideal of M2R? Whether it satisfies all the properties of ideals, both-sided ideals? Can somebody answer me? Is it both-sided ideal?
Yes, sir.
Yes. So yes. Okay. Now if I consider I2 equal to M2R, okay, that means I2 is nothing but the whole ring. So is M2 is I2 both-sided ideal? Of M2R? What will be your answer? Again, your answer will be yes, because it's the whole ring, so it must satisfy both-sided ideal properties. Now the idea is I need to find some ideal I3, and that should be both-sided, and that should be a both-sided ideal of M3 such that I3 should not be equal to I1 or I2. So that's our M. So to understand that, let us have a very nice property of ideal. So the property is, suppose I have an ideal ring R plus dot, and suppose the ring is with 1. That means 1R is there within the ring. That means R is a ring with identity 1R. Now suppose I is an ideal of R. Suppose I is an ideal of R. Okay. Now by any chance, suppose 1R is within R. Suppose 1R lies within I. Then what would be your conclusion? Any guess? What will be your conclusion? Any guess, somebody? If 1R, that means identity element of R, lies within I, the ideal of R, then what would be your conclusion? Any guess? Any comment? Anybody?
Sir, I and R are same.
Okay, so yes, absolutely. So the conclusion will be I should be equal to R. See, just only one element within that I will ensure that I and R must be the same. That means you cannot have a proper ideal I which will contain the identity element of R. So let us try to prove this. The proof is very easy. How? So I suddenly a subset of R, no doubt, because I is an ideal. By definition, I subset of R. So I need to prove, R is a subset of I. Okay. For that, let X belongs to R and R belongs to R. Okay. I will show. Okay. So let's X belongs to R. So I will show X belongs to I. Then what will imply? R is a subset of I. Then okay. Now X equal to, I can always write it 1R into X. Now have a look at. So 1R, it belongs to R. It belongs to R, and X is okay. So other way around. I will write it in a different way. I should write it X equal to X into 1R. I can write like this. Now see that this is from belongs to I, the ideal, and this is from R. Now from the definition of ideal, if something from I, if it is multiplied with the element of X, then that should be belongs to I, because that's the definition of ideal. What was the something? If I have something here and something here, for example, if I have, this is 1R and this is my X, so from the definition, if I multiply X into 1R from the definition of left ideal, since this is a both sided ideal, so it should also have the property of left ideal. So that should be from the definition of ideal, that should belongs to the set I. That means from the definition of ideal, that should be within I. That means X belongs to I, and that implies R is a subset of I. So as a result, hence R should be equal to I. So is it clear to all of you? Any question or doubt? If you have, I shall repeat it once again. Please don't be shy. If you find it not clear to you, please let me know so that I will again repeat that. Is it clear to all of you? Okay, so I assume that it's clear to all of you. Now I will come to the main problem, that I need to find some I3 which is not equal to I1 and I2. So this is my original problem. So I want to find both sided ideal of I M2, both sided ideals of M2, so that that should not be equal to I1 and that should not be equal to I2. Okay, that means some non-trivial ideals of M2R. Okay, let us have a look. So let I3 be an ideal. Ideal means both sided ideal of M2R such that, say, I3 not equal to I1. That means I3 is not equal to I1. So what was my I1? I1 was like this, all just a zero ideal. Okay, what does it mean then? I3 must have some non-zero element, then I3 must have some non-zero element. Say A, B, C, D belongs to M2R. Okay, now non-zero means at least one of the A, B, C, D is non-zero. So I claim that I3 must have an element, say PQRS, belongs to M2R such that P not equal to 0. See, first statement is says that it has some non-zero element. For example, it may have 0, 0, 0, 1, some non-zero element. But I claim that I3 must have a non-zero element such that this first entity has to be non-zero. Okay. So I need to first ensure that I3 must contain an element whose first entry is non-zero. How to do that? Okay. So few cases may appear. First, look at here ABCD was a non-zero element of this. Non-zero element means sum of ABCD must be non-zero. So case 1, suppose case 1. Suppose the non-zero element ABCD is such that A not equal to 0. So you have ABCD, which was the non-zero element of the ring. Then if this element is non-zero, then basically we are done. We are done for this claim, because the claim says that there exists a non-zero element with the first component is non-zero. So here this is the non-zero element among which the A0 is non-zero. In that case we are done basically. Then we are done. Now case 2. Suppose in ABCD B not equal to 0. So B is the element which is, so this is the element which is non-zero. But I need to show that by some means, by using some properties of the ideals, I need to show that this position should be non-zero. That means our aim is to, by some permutation and the properties of ideas, I need to put B here. If I can put B here such that then also this element will belong to I3, then we are basically done. Now have a look at this. Now, since as I mentioned, I3 is my ideal. So what was my claim? I assume that I3 be an ideal of M3R. So that means it's a both-sided ideal. Okay. So suppose I consider this element A, B, C, D multiplied with, see, this is an element of, this is an element of M2R, right? So this is an element of I3 where this is non-zero. So from the definition of ideal, this belongs to I3 because this is a right ideal, because this is a both-sided ideal, as I3 is both-sided ideal. Okay. So if I multiply with this element with this, then also it should be within I3. Then what is this multiplication? Can anybody tell me quickly? What is this multiplication? Can anybody tell me very quickly? This is B here, this is A here, this is D here, and this is C here. Now see, this was BD, so it came here, and this is AC, it came here. That means if I multiply with this matrix, just a permutation on the column of identity matrix from the right, then it actually gives you a column permutation on that matrix. So that's quite interesting. See, you sometimes it's very important to rotate your matrix, how to rotate your rows and columns. It's a very easy technique. If I multiply from the right with this matrix, so it's basically the on the right, if you have a permutated matrix over identity element, then if I multiplied it from the right, then that will give me an effect of column permutation on the whole matrix. So this belongs to I3. Now as you see that this element is non-zero, because initially I assume that B is non-zero, that means there exists an element B A D C belongs to I3 such that B is non-zero. So what I am actually step by step, case by case doing is that always trying to find a non-zero element at the initial place, because that will be required for my proof. Okay, so up to this that is done. Now I will look at case 3. Case 3, let in ABCD belongs to I3, C is non-zero. So what you need to do, by some permutations you have to put C here. If I will be able to move C from here to there, keeping the ideal property fixed, then we are basically done. So what to do for that? Just consider 0 1 1 0 and consider A B C D. If I multiply it with this, then what will be your matrix? You can see that this is C, this is D, this is A, and this is B, and that also belongs to I3. And so you can see that this element comes here. So I get an element such that the first component or the first position is non-zero. Now I have case 4. Similar way you can understand what could be the case 4. Let in ABCD belongs to I3, D is non-zero. Now what I need to do? I need to basically transfer D from here to here. I can do it step by step. First I can have a left, first I can have a column change from here to here, then D will come here, and then I can shift the row and then D will come here. So the simple way would be 0 1 1 0 multiplied with A B C D, and if I multiplied right side with 1 0, then ultimately you will find that it becomes D C B A. Okay, so you can check it. So at the end of the day, what I found that it becomes here, and this is non-zero. So we are done. So the claim was there exists a non-zero element. The claim was there exists a non-zero element such that this has to be non-zero. Like the first component has to be non-zero is done basically. So now I know that at the end of this proof, at least I can tell that okay, in I3 there exists an element. So conclusion would be, after up to this stage, the conclusion will be there exists an non-zero element PQRS in I3 such that P not equal to 0. Why I am emphasizing that there exists a non-zero element, it will be clear soon. What I am going to show now, let me explain you the idea, and now I think you will be able to guide me. So the idea is, I have already an element here which is in I3. Ultimate aim would be, by some means, by some steps, I will show that 1001 will belongs to I3. Then what would be my conclusion? After that, if I will be able to prove, up to this I have already done, then I need to prove few more steps. After these steps, my conclusion will be 1001. So that is my plan, whole plan. 1001 is within I3. Then what would be my conclusion? What would be my conclusion? Can somebody tell me? If I'll be able to prove 1001 belongs to I3, then what would be my conclusion? So this is the identity element of M2R. So then what would be my conclusion? My conclusion will be, yes,
I3 equal to M2R.
exactly. So I3 equal to M2R. So what I was trying to find, I have already seen I1, I have already seen I2, which was M2R, and I was trying to find I3, which should be different from both this, right? And at the end of the proof, we found that I could find I3, but I3 must be same as this. That means, except for I1 and M3, there exists no non-zero ideal of M2R, which is both sided. That means, at the end of this result, the conclusion would be M2R does not have any both sided ideal other than M2R and this, which is I1. So these two ideals are called trivial ideals. So in one line, the final conclusion would be M2R does not have does not have any non-trivial both sided ideals. Okay, so now the proofs are very simple. If you can think a bit about it, you will certainly be able to prove the or find the steps. So this step was crucial, where I found that this element is there. So first step would be, like, by some means and satisfying the properties of ideals, try to find how you can put this to be an element of I3. Then you can understand that you can, from here very easily, you can prove that 0001 belongs to I3, and then if you just add them up, because ideal is a subring, so you can very easily prove that 1001 belongs to I3. So this is the gap that I ask you to finish, and that will help you to give the final result. Okay, is it clear to all of you? Any question or comments? Well, good. So I am sure that you will able to prove this. Okay, this kind of rings are known as simple ring. Simple ring. So simple group, you heard about simple group, the same thing. No non-trivial ideal. That's why this is called simple. As I mentioned, the ideal concept and the normal subgroup concepts are same. So here, this is an example of a simple ring. Okay. Now, very quickly, maybe I'll ask you a question like, can you find a ring which is strictly in between? Some ring, I need to find some ring which is strictly in between Q, Z and Q. Okay, it may happen that there exists no such ring. What would be your conclusion? Can you find some ring which is strictly between R and Q? Quickly, can you give me some answer to this? A ring which is strictly between Z and Q. Anybody? Or your answer could be there exists no such ring. So can you find any ring R such that Z is a proper subring of R is a proper subring of Q, the ring of all rational numbers? Okay, the second question would be, now I consider a set A belongs to Z is S plus dot. With respect to usual addition and multiplication of matrices, a ring is S plus dot an integral domain is S plus dot a field. So this is very interesting. So you have to look at very carefully the set S, and then all the elements are A such that A belongs to J. So it's a, you can say that this is a subset of M to R. Now my question is this. So you need to give me the answer to these questions. Okay, quickly. Anybody? Anybody? I cannot hear you properly. Who is that? Okay, I cannot hear you properly. Somebody else?
স্যার
Somebody?
ফার্স্টের কোশ্চেনের অ্যানসারটা কি m বাই 3 টু দি পাওয়ার n হবে?
What? M?
বাই 3 টু দি পাওয়ার n, where m আর n are integers.
M by 3 to the power n, like this,
হ্যাঁ, yes.
such
m
that
and
M
n
belongs
are
to Z.
integers. হ্যাঁ।
Okay, maybe. So is it the unique answer you're talking about?
No sir, I have just thought.
One. Okay, fine. So we need to check whether this forms a ring or not. If that is so, then certainly your answer is right. So he has given one of the examples of a ring which is lying between strictly between Z and Q. Okay. So what's about the second answer? So you
So
can find more. Yes.
so we can take any integer and adjoin the inverse of that onto Z, and that gives us a ring that's between Z and Q.
So take any integer and then so you
Look
are
at
talking
Z
about
as
like this.
yes, sir. We are adjoining
Yes.
half to Z. Z adjoined half.
Okay. So what you are talking about Z plus half like this or better sense in that way, right?
Yes, sir.
Okay. That means A plus half Z such that half B such that AB belongs to Z. That is what you want to say, right?
Yes, sir. And this thing works for any integer instead of two.
Okay. So you can say this is 1 by n such that n greater than 1, n greater than 1, right? Or maybe a by b such that whatever, some rational number which is not an integer in that way. Okay, so there are plenty of such examples. Very good. Now, what's about question number 2? What's about question number 2? Okay, so I leave it this question as a kind of homework or your thinking. Maybe in the next class we shall discuss about it.